Hi everyone, my name is Cody Powers. It's April 11th, 2020. This is my video for case connection to Unit 2. I chose to do case 1 first, which states pyruvate kinase catalyzes the rate limiting step, the ATP generating step of glycolysis, in which PEP is converted to pyruvate. Multiple isoenzymes of pyruvate kinase exist in mammals. And then basically the questions ask, under normal conditions, describe all the ways in which pyruvate kinase is regulated in the cell. And then the second part kind of chats about how cancer cells manipulate glycolysis, and I'll get into that. But first, I just want to talk about glycolysis. There are three really big irreversible steps that would be glucose getting converted to glucose 6-phosphate by hexokinase or glucokinase, depending on if we're using the liver or just normal cells. Glucose 6-phosphate becomes fructose 6-phosphate, and then fructose 6-phosphate is then catalyzed by phosphofructokinase into fructose 1-bisphosphate, and that is another irreversible step. Later down the pathway, the third irreversible step is then phosphoenol pyruvate, which is catalyzed by pyruvate kinase into pyruvate. In the cell, pyruvate kinase, like I said, it's the last step in glycolysis. It's a rate-limiting step in glycolysis. All of these steps are sensitive to the energy states of the cell. More ATP in the cell, we're going to slow down glycolysis, and higher levels of AMP, we're actually going to speed up glycolysis. So let's see. Pyruvate kinase, it's highly regulated. It's allosterically activated by fructose 1,6-bisphosphate. It's kind of a feed-forward mechanism, so the more fructose 1,6-bisphosphate we have, we're going to allosterically activate pyruvate kinase. Pyruvate kinase is also modified by hormonal signaling, such as insulin and epinephrine and glucagon. Insulin is the dominant hormone in the fed state. It's going to speed up glycolysis. It's going to make us take the sugar out of the blood, get it into the cells. Whereas glucagon and epinephrine inhibit glycolysis, so it's going to slow down glycolysis. So with that, I'm going to read off my paper a little bit here. There's kind of long-term processes with regulating glycolysis, and there's quicker modifiers of glycolysis, and pyruvate kinase specifically, kind of like a longer pathway is how insulin synthesizes it controls enzymic activity through genetic expression. So basically, insulin will stimulate transcription of the gene that encodes it. So over time, the more glucose you have, the more pyruvate kinase is going to be expressed. Insulin also has allosteric effects on the enzyme. That being said, like the much more potent activator is fructose 1,6-bisphosphate. The cell is very sensitive to the ratio between ATP and AMP, so high levels of ATP indicates that the cell is in a high energy state, and high levels of AMP would indicate a low energy state. As ATP decreases and AMP increases, inhibition of PFK1 is relieved, and this leads to an increased concentration of fructose 1,6-bisphosphate. Fructose 1,6-bisphosphate causes allosteric modification of pyruvate kinase from an inactive form into an active form. And then of note, PFK1 is inhibition is also relieved by calcium that's made during muscle contraction. So when the muscles are working, we obviously need more energy. We need glycolysis. Calcium, when the muscles are doing work, you're going to start using more sugars. Okay. Also, allosteric little modification. PFK, pyruvate kinase, is also inhibited by certain things as well, one of them being alanine. In the fasting state, skeletal muscle exports large quantities of alanine through transamination of pyruvate in the muscle to alanine. This is then sent to the liver and is used as a substrate in gluconeogenesis, and then it's sent back to the muscle as glucose. And this is the glucose alanine cycle. So alanine is another metabolic signal that pyruvate kinase, to pyruvate kinase if the muscles are fasting, and then it reduces the activity of pyruvate kinase, so it doesn't cause hypoglycemia. Like I said, hormonal signaling also affects the blood levels. When blood sugar levels are low, glucagon is released, epinephrine is released. It interacts with the G protein complex. And then basically cyclic AMP acts as a second messenger, and it initiates many regulatory processes of the cell. One of which is the phosphorylation of pyruvate kinase, which causes the deactivation of pyruvate kinase. So in the fasting state, when glucagon and epi is high, we're inhibiting pyruvate kinase. We don't want to be taking glucose out of the blood and lowering the blood sugar even more. So in the fasting state, glucagon, cyclic AMP are all deactivating pyruvate kinase. Let's see, I don't know, look at my paper, just make sure I didn't lose anything here. So fructose 2,6-bisphosphate, when there's a lot of glucose, fructose phosphate can also be converted by PFK2 to fructose 2,6-bisphosphate, and fructose 2,6-bisphosphate actually increases the activity of PFK1. It's just another pathway. It's considered a shunt. It's not part of glycolysis, but it helps speed everything up. So just to reiterate, so insulin activates pyruvate kinase. Fructose 1,6-bisphosphate activates pyruvate kinase, and then glucagon, ATP, and alanine all downregulate glycolysis. The second part of the question talks about pyruvate kinase type M2, which I'll say PKM2, and then pyruvate kinase type 1, PKM1, and just how cancer cells use, how they express these different PKMs. Many types of cancer cells, it says, predominantly express the oncoprotein MYC. Interestingly, the oncoprotein MYC has been found to promote preferential expression of pyruvate kinase type M2 over type M1, which you would think was strange because PKM2 is actually inactive at typically stimulating PEP levels. So you would think that a cancer cell that's going to want tons of, it's going to want to speed up the glycolytic pathway, glycolysis, but it actually doesn't. So how this works is PKM2 is considered kind of inactive. It's not as activated by PEP as PKM1. So it doesn't participate as much in glycolysis, but it still participates in the breakdown of glucose. Basically, it's giving building blocks cellular energy to the tumor, and this helps that rapidly growing and dividing tumor cell. It gives it nutrients, so it prefers PKM2 because it doesn't give ATP, but it's actually giving the cell building blocks instead of energy production. PKM2 also prevents apoptosis, so usually when a cell goes to divide, if there isn't enough oxygen and nutrients, etc., it won't divide, it will go through apoptosis and just self-destruct. But PKM2 shuts off the mechanisms that stop cell division when energy resources are low. So basically PKM2 will always kind of like falsely report to the cell that there is enough energy to divide. So that cancer cell will keep dividing and it will never trigger apoptosis. So again, PKM2 is adventitious to the cancer cell just because PKM2 is providing nutrients for the cancer cell, and then it's also preventing apoptosis so the cell can continue to grow.